Hello, I'm Barry Sullivan, Program Director for the Electrical and Computer Engineering Department Heads Association. It's my pleasure to introduce this spotlight presentation by Carlo Manfredini, the R&D Director for EMONA Instruments, and Carlo will be speaking on Learning by Doing, Modeling Wireless Systems in the Lab. Carlo?
Thanks very much, Barry, for that introduction, and thank you everyone for being here. Last year when I came over, it was so close to home. It was only a 14-hour flight, and I was just saying this time Kim and John have upped the ante to see if I'm really interested in coming, and I had a 30-hour flight, 30-hour travel to get here. So I've come from Sydney, Australia, and I'm delighted to be here. So thanks for your time. I'm going to be talking about mathematical modelling with hands-on hardware. So let's just. So who is EMONA Instruments? EMONA was founded in the 70s in Sydney, Australia. EMONA is the Roman name for Ljubljana, which is the capital of Slovenia, where the founder of EMONA Instruments comes from. And we've been operating and making this educational equipment to teach telecommunications at the university level for 29 years now. So as I said, based in Sydney, we've been making our product, our flagship product, TIMS. Now TIMS stands for Telecommunication Instructional Modelling System. It was developed at the University of New South Wales to teach the very many topics that exist in telecommunications with one piece of equipment. So hence it's a modelling system. It's like Lego for telecommunications engineers. So since commercialisation, it's now in 40 countries throughout the US, and I'm one of the founding partners, and I've been doing this for 29 years. And so it's become sort of a life passion to try to deliver telecommunications teaching in the best possible way. So we suggest that whilst technology changes, principles remain the same. And so if we have a close look at this, in the very beginning of information theory, we had on-off keying. And some of you may remember this, or maybe not. Later on, valves were the next big thing, and so information theory was not that highly regarded. Then we started to get into electronic circuits miniaturization, and a lot of people still insist on building circuits with transistors and that in the lab, but we feel that that's maybe not the most efficient way to teach telecommunications. So now with FPGAs, you can't really see what you're working with, but we know what's inside them. They're full of block diagrams. So what's the future? We don't know. That's what's being discussed, and 5G and the DARPA talk yesterday gave us some indication of what's to come. It's very exciting. So how do we approach telecommunications? What we basically do is behind every telecommunication modulation scheme is the mathematics. It all starts with the maths and the theory. So the maths can be represented by a block diagram clearly, and there you can easily see the products, the addition, the phase shifts that make up QPSK. This block diagram, if we then replace each one of the blocks in the block diagram with a single hardware module, an electronic circuit, and on the right there you can see some of these circuits. We have simple elements, oscillators, adders, multipliers, phase shifters. Now these are the basic modules. So these are basic blocks, just like what you'll find in, say, Simulink or LabVIEW, but they're hardware blocks. So we have basic blocks. We have about 60 advanced blocks, which are encoders and modulators and spread spectrum devices, etc. And we also have DSP-type blocks. So here, for example, we can see a very introductory student using our equipment in action. He's doing amplitude modulation. And so you can see the adder, 2 inputs, 1 output, the 4-quadrant multiplier. And then down in the bottom corner, you can see 100 on the frequency counter. And what that's indicating is that our system's a modelling system. So it basically models the telecommunication at 100 kilohertz. So we can basically represent all the theory, but at 100 kilohertz. So the maths is the same at 100 kilohertz as it is at RF. But it's a lot easier for the, except scaled down, hence why we call it a modelling system. So the student can basically see the carrier and the message on a simple oscilloscope, and hence they get a more intuitive feeling of the experiment itself and what's happening in the lab. If we move to a more advanced experiment, there you can see the equipment set up with a number of modules, and we basically have a transmitter region where we have a few modules. We have a channel, we build the channel, so we basically model whatever channel we're interested in. We have a receiver, and then we have bit error rate instrumentation. So the student takes control of the experiment and builds it in an elemental way, which consolidates their fundamental understanding of what the mathematics is. So if we zoom in here, I'll just quickly just show a little video of this.
Increase the level of noise into the system beyond that threshold. Okay, now you can see errors are beginning.
Okay, so in that case, just a quick glimpse to show you the reality, the realism of the signals that the students are working with. So this methodology can be expressed as a transmission model. You've got encoding options, you have modulation options, channel options. It's an open architecture system, so you can introduce your own hardware, you can take your signals out, bounce them off a satellite, bring them back again. And ultimately, it's very open and available for expansion and staying up to date. So if we... here, for example, we have a student who, at this university, they initially only had simulation. After about 10 years, they came to us and said, we need to buy your equipment because the students aren't learning anything. They actually don't have any real fundamental understanding of what was going on. So they equipped the lab with the hardware. This student here in particular is doing some work with gold codes, and he's you know, had a really good experience using the hardware, and he's developed the algorithms in say MATLAB, and then implemented them on the hardware. So that would be an advanced example of a student having a good time with the hardware. Here are some comments from US-based professors that are more succinct than I can ever be. They're saying that while simulation does not create the feel of a physical system that one encounters with the TIMS system, they say that the construction of an actual system is a requirement to complement a simulation approach. So we take students from zero knowledge through to the point at which they can work purely on simulation. When they're more advanced students, they can handle the abstraction. So one comment that we got back was that when students make mistakes on simulators, they blame the software, but when they make mistakes on hardware, they have a look at their own efforts and kind of trust the hardware more. So that gives them a more tangible feedback. They make it smoke, as a professor once said to me. So the equipment comes with 2,500 pages of experiments. We're constantly adding it over the years. And our experiments tend to be organised by wireless standards, and different wireless standards have got different modulation schemes. We cover very many of them. I'm just going to whiz through these because I have some new information that I want to present. Some of our experiments, like I said, 2,500 pages of turnkey documentation. Or you can customise the labs to suit your requirements. So I'll be at the booth so you can have a closer look at these later on. So we have three modes of delivery: hands-on hardware, remote control hardware, and simulation. So in the hands-on hardware area, we have our flagship product, the TIMS unit. We also have signals and systems experiments because we believe that signals and systems is so fundamental, students need a hands-on experience. So we get them building convolution, IIR structures, understanding the spectrum, Fourier analysis with real hardware signals. I'll just move on to the next one. There's a video there, but I'm going to skip it because I'm concerned about running out of time. We have fibre optic modules. So the TIMS unit can be a bridge to your more advanced fibre optic courses using optical couplers and simple LED lights, wave division multiplexing, and very many other important introductory topics. We have DSP modules now, and the DSP modules are useful for doing Viterbi decoding and OFDM, digital filters, etc. So they're very open-ended, and they live alongside the other modules. Now, here's something new and interesting that we're doing. So we've implemented OFDM on the DSP, And we've implemented it at 100 kilohertz. So you can see we have 20 subcarriers and centered at 100 kilohertz. The student, on the left you can see the block diagram, and on the right you can see the module, the patching diagram of the modules, and you can see that we actually get the student to build a quadrature modulator. So the DSP implements the OFDM modulation, comes out of the DAX into the quadrature modulator. You build the channel you're interested in studying. It might be a multipath channel, bandpass channel, a fading channel, whatever. You just choose the modules you're interested in using and back out again and into the instrumentation. To make it a real experience, there's an equalization stage, and we use a LabVIEW-based GUI, which allows you to enter in pilot signals and then calculate the equalization response needed for that particular channel and feed it back into the equalizer. So it's very comprehensive and yet hands-on, and it really makes important concepts like OFDM seem really quite straightforward and very accessible to the student. We have a small unit called a biscuit, which is a lower cost unit. And we also make boards for the NI Elvis. We're a partner with National Instruments. Okay, and our remote hardware, which appears to be very popular in China at the moment. My colleagues just come back from there and they're quite interested in this kind of thing. We also have some customers in the Middle East who are using our remote hardware because it allows students to do experiments without coming into the university when there's troubled times. And basically what we've done is we've taken away the knobs and switches and we control the equipment remotely across the internet, and we have a situation where you can have 20 or 30 students logged on to the same experiment at the one time. The unit time shares itself. So it's a very handy way of giving your distance students some access to the lab 24 hours a day, 7 days a week. And so if you come to the expo floor, you can see a demo of that, or even better, you could get out your tablet or your mobile phone, log into our live server that's in Sydney any time, and just play around with that equipment that's live. As well, we have a simulator, and our simulator has been made to avoid programming entirely. So we believe that simulation is very useful as pre-lab learning and as a complement to hands-on hardware. And so what we do is we have mimicked the hardware. So you just place the modules, wire them together, and take measurements. So this is available to all students as a site-wide license. And so finally, things that we're working at incorporating into our system, software-defined radio via our DSP modules, interfacing to GNU. We have some people working on some MIMO, modelling of MIMO systems down at 100 kilohertz, reconfigurable DSP blocks. So the modular approach, the hands-on approach, we feel it's very practical. It's, the students really love it. They like to be in control, and they like to be able to do something in the lab and make mistakes and learn from their mistakes. So I guess overall my take-home message is mathematical modelling with real-world signals to complement any simulation work that you're doing. A block diagram approach is always relevant because we think in terms of block diagrams, we represent our systems in block diagrams. So no matter what the technology is of the day, thinking in that way is always going to be important. Multiple experiments in one system rather than having lots of boxes to deal with. Expandable, customizable, modular, open, you can make your own modules, and we encourage that. Highly student resistant, and by that I mean we have never charged for service in the 28 years that we've been making the product. The product is very reliable. We have so few returns from our worldwide market that we don't even bother to ask you to raise an invoice to repair it if you do send something back to us. Very reliable. Students enjoy learning by doing, and deliverable by multiple mediums. The wine glass is to remind me to say, last year I brought a nice bottle of wine to Napa Valley to give away. This year I brought a lovely 2008 Shiraz from McLaren Vale. So please come by the booth and enter in the draw for that bottle of wine to enjoy on the golf course. So thanks very much for your time.